Welcome to Calculus. Today we will investigate finding limits of trigonometric functions, focusing on using trigonometric identities and algebraic strategy to calculate these limits. Let's take a look at 4 examples. Let's head over to our notes screen. So here's our first example. It says evaluate each limit algebraically. So the strategy we want to use, if we think about strategies we've used already, we've used direct substitution, we've used tables to estimate the limit, the value of a limit. We've also graphed, but here we want to use an algebraic strategy. So the one we're looking at is the limit as x approaches 0 of sine of x over 7x. Now we've seen this limit before when we were trying to create continuous functions. Let's see what happens when we run direct substitution. So just as a rule of thumb, if you can try direct substitution, that's a good place to start. So I'm just going to drop the limit and then substitute 0 for x. So sine of 0 over 7 times 0. So let's just remember on unit circle, at 0 radians, the sine value, so again, sine of theta or x is the y over the radius. So at 0, let's go ahead and change theta to 0. That would be equal to 0 over 1, because if you think at the x-axis, the height of that right triangle is 0. It's kind of a special case right triangle that looks like a line segment. So what that tells me is that this becomes 0 over 7 times 0 is 0, and dun, 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 that's the indeterminate form. So the direct substitution doesn't get us very far. It just tells us, hey, you got 0 over 0, you got to try something else. Cannot divide by 0. Well, let's recall what we saw with the graphical approach to sine of x over x. So I know that this one's a little different. It's sine of x over 7x. So I just want to take a moment to head over to Desmos just to check out again what is the graphical interpretation of the limit as x approaches 0 of the function sine of x divided by x. So recall we've looked at this one before. We'll zoom in a little bit. So what we're looking at right here is what's happening to the y value as x gets close to 0 from the left. So from the left, as I approach the y-axis, the y value is like 0.994, 0.995, 0.998, really 0.999, 1. So the calculator's kind of, it's so close to 1 that it's estimating it is 1. When I get to 0, it is undefined. So that kind of supports what we'd seen. So from the left, it's going to 1. If we check from the right, so I'm going to back up and then kind of come back up towards the y-axis from the right-hand side. So 0.997, 0.998, 0.999, 1, and then undefined. So even though it's undefined at the x value of 0, the limit as we approach 0 is definitely 1. And a lot of times in calculus textbooks, that's given as a theorem. So what we need to do is we need to bring that as kind of just a fact. We'll just label it theorem. And basically the statement is, if you got this function sine of x over x, and you want to take the limit as x approaches 0, it's going to equal 1. Now, how can we use that to deal with what we've got here, which is the limit as x approaches 0 of sine of x over 7? x. So here's the strategy. What I'm going to do is I'm going to take this, this limit and this function, and I'm going to apply one of these properties of limits. And what I'm going to do essentially is I'm going to pull off the 7 as a fraction. So it is in the denominator. So the way I'm going to pull it away from the sine of x over x is as 1 over 7 times sine of x over x. One of the properties of limits is that if you've got a constant that's a multiplier that's with the function, we're able to pull that constant out to the left side of the limit. So this limit as x approaches 0 of 1 over 7 times sine of x over x, really it's equivalent to 1 over 7 times the limit as x approaches 0 of sine of x over x. Now, how does that help us? Well, if I apply this red theorem, this whole limit, if I can get that kind of isolated from whatever limit I'm trying to take, I can say that that equals 1. And all of a sudden, this kind of just falls into place. This whole expression becomes 1 over 7 times 1, and automatically it's solved. The limit of this function as x approaches 0 of sine of x over 7x is 1 over 7. So knowing that theorem, which we've kind of seen graphically, we've used it before, helps us as an algebraic strategy. If I can transform a given function into that sine of x over x, then I can use it really as a substitution. The limit as x approaches 0 of sine of x over x is 1. Well, let's take a look at another one. So this is kind of similar numbers, but just different places. Here's the limit as x approaches 0 of sine of 7x over x. So the 7 has moved. I think we're going to run into the same problem with direct substitution. We can try it because it is good to try it always initially. If you can find the limit that way, it's kind of the most efficient. So I'm just going to back up because I don't need that limit. Remember, when you're doing direct substitution, you drop the limit and you say sine of 7 times 0 over 0. So automatically I've got a problem. And then sine of 7 times 0 is the same as sine of 0, which again is 0 over 0. Indeterminate form. But that's okay. So we're starting to get to the point to where seeing the indeterminate form isn't a crisis. It's just a call to some other strategy. So on this strategy, what I need to do is I need to introduce something down below. Now, what I need to know is this. So let's just remember our theorem. So just to recall, we've just seen it. The limit as x approaches 0 of sine of x over x equals 1. Now, here's the deal. The limit, I'm going to do a few examples here, see if you can catch the pattern. This limit as x approaches 0 of sine of 2x over 2x. What do you think that equals? 1. Let me give another example. So the limit as x approaches 0 of sine of pi x over pi x is, you guessed it, 1. So if I can make the angle part of the sine, whether it's x or 2x, pi x, 7x, the same as what I'm dividing in the denominator, that fulfills kind of the requirement of the theorem, and it also equals 1. Now, how can that help us here on the question we're looking at? So if I've got sine of 7x over x, the way I want to rewrite this is by introducing the missing constant multiplier in the denominator. So I see that this is sine of 7x, and I've got an x down below, so what do I need to incorporate there? Excellent, I need to incorporate a 7. Now, it's not for me to just be placing 7s in any denominator. However, remember from what we had done with conjugate multiplication, I can multiply by something over itself, because remember that has the value of 1. So if I can multiply, I'm going to back up here, and I'm going to multiply this entire function within the limit by 7 over 7. And the idea here is I'm going to let the upper 7 kind of chill for a little bit. It's just going to stay right there. The lower 7 needs to go in its useful place. So let's write what's left. So now I've got the limit as x approaches 0 of the chilling 7 times sine of 7x over the moved 7 times x. So it's starting to look really promising. What I need to do at this point is I need to let this constant migrate out in front of the limit. So just like we saw with that last question, previous question, we let 1/7 kind of, or whatever that was. Let's look and see. Yeah, 1 over 7. I let it migrate out to the left side of the limit. We're going to do the same here with that 7 that we let chill for a moment. So this becomes 7 times the limit let me catch up, my pen is glitching. So 7 times the limit as x approaches 0 of sine of 7x over, and I got to keep this color coded because I want you to just kind of track what has gone where. And at that point, what I can say is that this whole limit, based on my theorem and those other examples, what's its value? Good. It becomes just 1. And the simplification is real straightforward from here. This is 7 times 1, which is 7, and boom, this is complete. We found the limit of the function. As x approaches 0 for sine of 7x over x, it equals 7. The y value comes to 7 from the left and from the right. So definitely keeping this theorem kind of handy, and kind of its variations, so the green ones, it's very useful when calculating these trigonometric limits. If I can make it look like those, then I have kind of an immediate substitution of 1. Well, let's see something that's a little more involved. Here's the limit as x approaches 0 of sine of 5x over sine of 2x. Now, what we've got going on here is 2 occurrences of sine, and the one that we're kind of okay with is this one in the numerator. We really have to think about, what do I do with this sine of 2x in the denominator? That's kind of a puzzle at first. So we'll begin again by just saying, what's the way that we can make this look like our theorem? So I'm going to bring that theorem here just to kind of emphasize its kind of central role as we do these trig limits. So limit as x approaches 0 of sine of x over x equals 1. Well, I basically, I need to treat this as two of these sine of x is over x. So my initial step here is going to be to separate that numerator and denominator. So I'm going to write limit as x approaches 0 of sine of 5x over something. Now I'm just going to hold that there because I need to fill that in with something, but I'm just going to leave it as a blank right now. Times something over sine of 2x. So notice my first strategy there is just to separate the numerator and the denominator. They got to be separated. They're like children that are fighting. You got to move them apart. So I need to think about what should go where. So I have a feeling that right here, remember the descendants of this theorem. If I put 5x there, that limit will equal 1. So I've done that, but I need to kind of back up a little bit and do it properly. So out front here, I need to multiply this by 5x over 5x. Now, I'm going to let that denominator 5x move. I'm going to let it move underneath that original green sign of 5x. The 5 in the numerator, I want to let it move out front, like we did with the 1/7 and then the 7 in the two previous examples. And in that case, like that gets that first fraction in a manageable form. It will look like our theorem, and we can evaluate that limit to equal 1. But I have to also think about what's going on with this other fraction over here. So the idea is I want to pick up and think about what should I put there, and then think like I'm going to try to flip that fraction over so it looks like our theorem. So if it were flipped over, what should be in the top that would flip and be on the denominator? So definitely that should be 2x, correct? To match what's here is the angle of sine. Well, again, let me back up and do it properly. So I'm going to get rid of that 2x because I have an x that's kind of spare here. That x has not been allocated. So what I'm going to do is I'm going to take that x and put it there. And then I need to think, what else had I tried to place there? Well, it was 2 over 2. And I'm going to put that right here, 2 over 2. So we kind of got a lot of arrows flying all over the place. But that 2 needs to go with the x to supply a 2x there. And then the only other piece to like keep track of is this denominator 2. I'm going to move that out front with the 5. So that's kind of the strategy. Notice, like, just to recap, like what I've tried to do is separate the numerator and the denominator, and then figure out what needs to go underneath, what needs to go above, to make them look kind of like this theorem and its descendants, where I've just got the same 5x over 5x, 2x over 2x, so forth. So let's do that. Let's make those changes. So I'm going to try to keep this color coded as we go. So this becomes 5 over 2. So we've moved those pieces that were drawn arrows out front of the limit, or times the limit as x approaches 0, of sine of 5x over, from the blue, 5x. And then for that second fraction, times, I'll put the denominator sine of 2x, and in the numerator, I have a red 2. and that spare blue x. At that point, we need to use another property of limits that we hadn't used so far. If I've got two fractions, really two terms, any two terms that I'm multiplying together within a limit, one thing that I can do to kind of separate my work is record it. Guys, I'm going to go all to green now. Record it as two separate limits. So this is 5/2 times the limit as x approaches 0 of sine of 5x over 5x times, so instead of just multiplying times 2x over sine of 2x, this is the limit as x approaches 0 of 2x over sine of 2x. So that's a property of limits. If I got a limit of something times something, it's equal to the limit of that first thing times the limit of the second thing. We can separate them like that. What's the advantage? Automatically, we see that that first limit has the value of 1. Now, that'll let me at this point deal with kind of a simplified version. This is now 5/2 times 1. And I now need to deal with this last fraction. So it is kind of upside down. Now, the idea here is I can do this, the limit of this fraction flipped over, sine of 2x over 2x. And what I'm going to do is I'm going to write it with the -1 exponent. So 2x over sine of 2x is equivalent to sine of 2x over 2x to the power of -1. Remember, the negative exponent is just a reciprocal maker. So if I raise it to the power of -1, really it just flips over the fraction. What advantage is that? What that lets me do at this point is say 5/2 times 1. So a third property of limits, we're catching some properties here, is that if I have limit of something to a power, it's the same as that whole limit to that power, but now within the parentheses. And once I do that, again, what I've kind of isolated there is this theorem. Really, it's one of the children of the theorem, that equals 1. So this is all kind of reduced down to 5/2 times 1 times 1 to the power of -1. Well, the nice thing about flipping 1 over 1 is the same thing as 1 over 1. So this is really just 5/2 times 1 times 1. And this is all just down to 5/2. And if you'd like a decimal, 5 divided by 2 is 2.5. Kind of neat the way that that fraction has the same values in the decimal. That's unique. 5 over 2 equals 2.5. All right, so that used a lot of different strategies and a lot of different properties of limits. Notice though that it all does kind of revolve around that theorem. Limit as x approaches 0 of sine of x over x equals 1. Let's take a look at one final example that involves another theorem. So one thing that we see, so this one's different. It's cosine of 4x minus 1 over 2x. We're interested in the limit as x approaches 0. So that doesn't look like our sine of x over x. What we need is a separate limit. So I'm going to pull, and this is another theorem. So all these theorems are named right here in these examples. We're just going to identify them as theorems. And basically what we can say, if you think back to geometry, you got a theorem. Once it's been proved, you can use it kind of as a result within any problem that you're trying to complete. So the theorem goes like this: the limit as x approaches 0 of cosine of x minus 1 over x equals something. So what I'd like to do is just look at that function on Desmos just to investigate it graphically. And I do want to kind of make one of these descendants. So we'll pick that lava color just since it's related. The limit as x approaches 0 of 1 minus cosine of x over x equals. I want to see, are those different or are they the same limit? So let's head over to Desmos. Again, we're just going there to see what does it look like graphically. Because as you can see, if I divide that by 0, I'm going to get indeterminate forms again. So I'm going to type in here f of x equals cosine x minus 1 over x. And let's go ahead and type in, well, I'm going to pause there. We'll type in the one that's flipped around in a moment. So I'm going to go directly to 0 to begin. And what I'm seeing when I go directly to 0 is that it's undefined. So if we did direct substitution on that cosine x minus 1 over x with 0, it would be indeterminate, 0 over 0. But what we can see on the graph is that I approach that, really that left-hand limit as x gets close to 0, the y value also gets very close to 0. So it's getting smaller and smaller and smaller. I reach 0, it's undefined. From the left or from the right-hand side, it shows the same. As I approach 0 from the right, the y values get closer and closer to 0 themselves, and then it hits that undefined spot right at the origin. Now, that leads me to say that the limit of that as x approaches 0 is 0. What about the other version? G of x equals 1 minus cosine x over x. So really all that is a reflection in the x-axis or the y-axis, whichever way you want to think about it. And it shows the same exact property. It does have the reflection, but as I get close to the origin, so here I'm on the blue curve, it also is undefined at the origin because it's the indeterminate form. But the limit as I approach from the left and from the right is 0. So that confirms that, that second theorem that we've got. Well, let's take that knowledge back to our notes. And let's fill these theorems in. So this first theorem definitely equals 0, as does the second. Now, let's use that here with this kind of variation. So I got here, the limit as x approaches 0 of cosine of 4x minus 1 over 2x. We want to find that. So if I tried direct substitution, it's going to be 0 over 0. Let's just show that real quick, since this is a different example. So that would be cosine of 4 times 0 minus 1 over 2 times 0. And let's evaluate cosine of 4 times 0. So that's cosine at 0. So on unit circle, cosine is cosine of 0. Well, theta generally is x over r. So it's that horizontal piece over the radius. Well, at 0, those are the same. They're both 1. So if I can get rid of that central part of theta and just make it 0, that's going to be 1 over 1. So cosine 0 is 1, so that becomes 1 minus 1, oops, over 0, oop, that's 0 over 0, indeterminate form. So the direct substitution does fail us. So we just say, okay, we're going to keep moving with our math life, and we'll try something else. Now, keep in mind for this rule, I need this to be just like with the sine of x over x. If it's a descendant, it needs to have the same. So if it's 4x above, it needs to be 4x below. So my strategy with this one is going to be to introduce a product or a factor of 2 down below so that that becomes 4x. Well, let's not get too far ahead of ourselves. So what I'm going to do is I'm going to write this kind of with that factor introduced, but more carefully. So limit as x approaches 0, leave some space, cosine of 4x minus 1 over 2x. So again, I know that I need a factor of 2 down below here so that that's 2 times 2 or 4 to match with the 4x above. So I'm going to put that 2 out front, but again, I need to multiply by something divided by itself. So that's 2 divided by 2. And let's just track where those 2's are going to migrate. This lower one's going to migrate over to multiply with 2x. Where do you think the numerator 2 should go? Yeah, excellent. So according to properties of limits, it's going to migrate out in front of the limit. So this equals, keep it color coded, 2 times the limit of as x approaches 1. I'm sorry, limit as x approaches 0 of cosine of 4x minus 1 over 2, that red 2 times 2x. I'm going to let it all go to green here. So this is now 2 times the limit as x approaches 0 of cosine of 4x minus 1 over 4x. Oops, my parentheses wrong there. We'll fix it. And that's over 4x. So the red 2 times the green 2 is a 4. What's that an advantage for us? Well, that, just like my theorems here, equals 0. So this becomes simply 2 times 0 or 0. And I'm going to box that. All right, so that's our fourth example for these limits of trigonometric functions. Thank you for joining for these 4 examples. We are going to need more trigonometric identities to solve all the questions that you're working on. So I'm going to zoom up real quick and kind of give a recap about what's important in terms of theorems and identities. So like you can predict already, our limit as x approaches 0 of sine x over x, that's one of these essential tools. That equals 1. We also know that the limit as x approaches 0 of cosine of x minus 1 over x is the same as the limit as x approaches 0 of 1 minus cosine of x over x. Both of those equal 0. Another set of facts that you really want to keep right at hand are these trig identities. So we've used kind of just sine and cosine, but what you'll run into is tangent of x. And the identity you want to remember with tangent of x is that it equals sine of x over cosine of x. That's from trigonometry. You'll also need to remember that cotangent of x, remember that's the inverse of tangent, is not surprisingly cosine of x over sine of x. And then there's 2 others. Secant of x is 1 over cosine of x. And then the last identity that's useful for us is cosecant of x is 1 over sine of x. So I just want to offer these identities here. The two limits on the left, those are from calculus. And we've kind of informally demonstrated them. We haven't proved them, but we've got them there to use. And then the 4 green ones, those are from trigonometry. And we'll definitely need to use those in these other problems that you're working on. Thank you for joining. So I'm going to sign off for now. I look forward to working with you on these limits of trigonometric functions. Thank you for joining. See you soon.